Thank you for a kind introduction. Okay. So jumping spiders are agile hunters. So they can jump 6 times longer as their body length, and the maximum speed is very fast. And because they use a hemorrhage-based hydraulic actuation, their kinematic is unique. And also they can control very strong adhesion force to jump horizontally. So in this research, we would like to measure the ground reaction force, like the generated force on the foot, and to quantify the locomotion. And the sensor consists from 6 plates, as you can see. And we employ the sampling Moiré method as an analyzing technique. And we also use a line scan camera as a measurement instrument. So these are the conventional devices to measure the ground reaction force. These are called force plate. It's kind of a plate-shaped force measurement devices. And both are successfully measuring the, for example, this is a triaxial, and that one is a biaxial force measurement. But why there are some negative points, like it's hard to make smaller because it's a hand fabrication, and also the MEMS one is kind of fragile and difficult to fabricate. Therefore, recently, triaxial force plate array is proposed by using the sampling Moiré method. The devices consist from mechanical part and optical part. Let me talk about the mechanical part first. So there are plates and supported with a spring, and the spring has a gradient pattern on the backside. So when the leg pushes the plate and the plate is displaced, and the optical system captures the triaxial displacement to calculate the force, like this. So how triaxial displacement is measured? So this is the optical configuration. So as you can see, the pattern is observed by left side and right side of the prism. And when the force is applied, as you can see, the pattern moves depends on the force, so that we are able to measure the force, triaxial force simultaneously with 9 places. And since the sampling Moiré method is an analyzing technique using the periodic pattern like this, and the sampling Moiré method is able to calculate displacement with this precision. But as you can see, when we want to do the array configuration, high resolution camera is required. But at the same time, when we want to measure the spider, it's kind of a very quick locomotor. High-speed camera is also essential. Therefore, we would like to introduce the line scan camera. So that, as you can see, the line scan camera has a wide scanning area with very high speed compared to like a conventional cameras, like a high resolution camera and high speed cameras. So we can say that it is suitable for array and both array and high temporal resolution. But there is a problem. So the problem is that when we use these kind of periodic patterns, it is impossible to measure this y directional force, I mean the upward force, like this. So now we would like to introduce the tilted pattern instead of normal straight patterns. So let me introduce the how to get the triaxial information from just one line. When the Fx force is applied, the prism images moves to the same direction, and the camera images also moves to the same direction. While the Fy force is applied, these images moves up, and this is important. the camera images move alternately. And finally, when the FZ force is applied, the images are moving toward the center. In order to distinguish these three forces, we defined four capturing areas: 1, 2, 3, 4. And since these capturing areas has different moving directions, we are able to measure the triaxial force simultaneously. And this is the design of the force plate. And these are the required specifications. And we operated the line-scan camera at 4 kilohertz. And as you can see, there are 6 plates, and one plate is corresponding to a pair of legs, and so it is sufficient for 8 legs animals. And this is the detail of the design. As you can see, the plate is supported by 2 springs like this, with a 70 micrometer thickness, and it's made of a 70 micrometer thick glass plate. And on the backside, the tilted pattern with a 100 micrometer pitch is formed by using the like a simple patterning. And as you can see, since there are 6 plates, which means there are 6 images, and through the prism, the images are duplicated into 12 patterns, and like this. And after the design, we conducted the simulation, and from the simulation, we could get the spring constant, and from the spring constant, we calculated the calibration matrix, which is kind of a relationship between the force and displacement. And this is the fabrication. It's very simple. First, the patterning, the aluminum, and then the substrate is cut by using the UV laser. And this is the fabricated device that you can see the fine pattern is deposited on the backside. And after the laser cutting, you can see the fine spring is also fabricated as designed. Next, this is the experimental setup. As you can see, there is a high-speed camera for the spider spider recording, and there is also a line-scan camera with a telecentric lens. We employed telecentric lens to avoid the distortion. And the force plate array was put on the prism like this. And next, I'd like to talk about the calibration. Calibration was conducted for each plate with each axial force. And as you can see, the 12 images are clearly recorded by the line-scan camera. And this is the calibration result. And when the FX force is applied, you can see the same direction displacement are confirmed. Alternate displacement are confirmed for the Fy, and when the Fz, the moving toward the center displacement is confirmed like this as designed. And the similar trend was observed as simulated, and force resolution was confirmed like this. Next, we conducted a ground reaction force measurement of a jumping spider. So as you can see, there's a fabricated force plate, and the spider literally just walks to the force plate, and we waited until he intended to jump. So it takes a patience, okay? And this is the final result. Okay. As you can see, the fourth leg is placed on the plate 2, while the third legs are placed on the plate 4 and 5. So I just put these 3 graphs. And you can see there's a very huge shear force for the fourth leg, and please check it. Oh. Can I try again? Next time it's worse. So the strong shear force was confirmed for the fourth leg, and it was fit the previous research. And also, I want to mention about the unique dual peaks for the third leg. Here. So I stopped the first peak and the body and the second peak. So the first peak was corresponding to the fourth leg's locomotion, which means that the third legs are acting as a pivot point of the locomotion, and the second peak was appeared as because of the locomotion of the third leg. I'd like to conclude that the fabricated force plate array demonstrated simultaneous triaxial force measurement with design responses, and the force plate array was operated at 4 kHz, and the strong shear force and unique double peaks are confirmed. Thank you for your attention, and thank you for the support.